So we're going to look at ordinary differential equations, or ODEs for short, ordinary differential equations. First of all, I know it's an ordinary differential equation. If it's an equation, it's got an equals sign. So if the thing I'm looking at has got an equals sign in it, then it's an equation. Something equals something. If it's got a differential in it, if it involves some sort of differential, in other words, something like dy by dx, so we've got this differential and it's an equation and it's ordinary. We call it an ordinary differential if you've only got one independent variable. And we'll need to just remind ourselves about what we mean by an independent variable. X, say. So that's an example of an ordinary differential equation. There's two of them here, look. This is an equation because it's got an equals sign in it. It's a differential equation because it's got a differential in it. And remember the two conventions for a differential, either a prime or dy by dx. This is the dependent variable, so I can label that as the dependent variable, y. And x is the independent variable. The words are really weird, so I'll just synchronize it up. Okay, so we've got the independent and the dependent variables, and you can see them here, look. We've talked about this before. So if we've got a function that involves an independent and a dependent variable, then the independent variable tends to go on the x-axis and the dependent variable at the y-axis. So the solution to an ordinary differential equation is a function which holds true for a range of values for x that we need to stipulate. So what we're going to do is determine what sort of differential equation it is, and we'll start off with first order differential equations, and they're always going to be ordinary ones. In other words, they've only got one independent variable x in them. And we're going to investigate how we solve them and how we come up with, discuss a range of values for which these things are true. So, just a little introduction. Science and engineering uses modelling to make predictions and understand the process. So, this involves differential equations. A model almost always involves a differential equation because it almost always involves a change. And if there's a change, we talked about before in differentiation, a change is associated with differentials. So we end up with a model that is in fact a differential equation. So what we do is we sort of write our model in terms of an equation, a differential equation, which we then try and solve. I've written some examples down. There's a very familiar formula, F equals ma. And if we look at it, t is the independent variable, so it's a time-dependent function, and f is our dependent variable. So the force is the dependent variable, t, the time, is the independent variable. And the mass is dependent on the velocity, the acceleration. We can write the acceleration as dv by dt. So it's a differential. That's in fact a differential equation. I could think of the velocity as the differential of displacement. So I can write actually the acceleration as the second differential of displacement. So if I differentiate the acceleration once, I get the velocity. If I differentiate it again, I get the displacement. So the second differential will give us the acceleration. And so I've got this. And this is a second order. Ordinary, because there's only one independent variable, time, differential equation. Here's another one. If we consider a mass falling due to gravity, here it is coming down, and it's feeling the acceleration due to gravity, and that's this bit, mg. So this is its weight. This is gravity pulling it down. But that's not the only force it feels. It also feels this force. And this force is a function of the velocity. If the velocity of this thing changes, the size of this force is going to increase. So what would this be standing for? What would this be representing? As an object falls and its velocity increases, it's going to feel not only the acceleration due to gravity, but another force acting the other way, which would be the resistance of the air, exactly. Air resistance, which is a function of velocity. The faster I go, the greater that air resistance will be. And that's acting in the other direction. So I to subtract it from the force, that's the gravitational force. So I get mg minus kv. I get to the point where I reach terminal velocity, and what would that be? When would that be? When would that happen? Right, and at that point, what would be true about those forces? They would be equal and opposite, wouldn't they? So the air resistance would exactly balance out the force due to gravity, and the thing would fall at a constant velocity. So mg and kv would be equal, so the overall force would be 0. Well, I can write this as mg minus k ds by dt, where s is the displacement as this thing's falling. And so I can turn it into a differential equation. So that's another example of a differential equation. But this time the force would be a function of displacement. So those are examples of ordinary differential equations, and we can try and solve these things to come up with functions to describe how this thing is moving. And what we need to do is to be able to look at some techniques for solving differential equations, and then we can come back and have a look at a few models and see, apply it. So let's look at some general techniques. For example, so let's consider something like this. dy by dx equals x squared y. This is telling me what the dependent and the independent variables are, dy by dx. So if we've got a differential, y is the dependent variable and x is the independent. So I know straight away what they are. I've only got x as the independent variable, so it's an ordinary. It's a differential equation because it's got a differential in it, and it's an equation because of the equal sign. So it's a differential equation that we can solve. Here it is written using the convention for y prime for the differential. If the dependent and the independent variables are multiplied or divided, and in this case they're multiplied, then we can solve by separation of variables, and that's the most common method for solving first order differential equations. Separation of variables, so we're going to focus on that. In other words, they're multiplied and divided. This, for example, is an example of something that's not a differential equation that can be solved using separation of variables, because the x squared and the y are not multiplied together, they're added. So I couldn't use this technique in an example like that. But I can in an example like this, because they're multiplied together. So let's have a look at this. dy by dx equals x squared y. And what we're going to do is separate the variables. Solve by separating variables. So what that involves is taking the dx, and we think of this like we did when we were thinking about integration by substitution and things like that. We treat this dx now like a term, so we can actually multiply effectively both sides by dx and shift the dx up there, so we'll have dy one side, dx the other. And then we try and get all the terms involving x on the side with the dx, so over here, and all terms involving y over here with the dy. So we separate the variables. We have the y's on one side, generally on the left, and x's on the other side. That's what we mean by separating the variables. So I write that dy times 1 over y, or 1 over y dy, equals x squared dx. I've separated the variables. And now I just integrate both sides. I integrate the left-hand side with respect to y and the right-hand side with respect to x. So in other words, I've got an integration to do. If we think back to differential equations, all the differential equations we've looked at so far involving a differential. How do I get rid of a differential? How do I undo a differential? I integrate. So we've not left integrations behind. We're going to be using the same techniques we've been looking at so far to help us solve differential equations. So we will be integrating. So what do I do to solve this? I integrate both sides. Integrate the left-hand side with respect to x and the right-hand side with respect to y. Well, we can do that virtually by inspection, because we know what the integral of 1 over y is. It's log y. And we know what the integral of x squared is. Add 1 to the power, divide by the new power. X cubed over 3. Yeah. Don't mix up differentiation and integrating. And then what do we add at the end? Plus c. Okay. We've got a c on this side as well, of course. To both sides we add c, but again we just consolidate all our c's into one big c and put that at the end on the right hand side. So that's the solution to our differential equation. This is an implicit solution. What we mean by an implicit solution is that although we've got something like y equals, I haven't got y, I've got log y. So if I can rewrite this equation, this final answer in y, the dependent variable, equals, so if I can get my final function, my solution in other words, which is this solution here, to look like y equals something, and then I've got what's called the explicit solution. Because what I really want is the relationship between the dependent variable y and the independent variable x. Well, it's here, but it's implied. It's not strictly in terms of y equals something, so we call it an implicit solution. And if I want to get the explicit solution, what I do now is try and get y equals something. Well, if we think if we've got log y, what's the inverse function to the natural logarithm of y? It's e to the. So we take e to the log y equals e to the x cubed over 3 plus c. So we take e to the both sides effectively. But these functions are opposites to each other. E to the log something is just y. So that actually gives us y equals e to the x cubed over 3 plus c. So it can be a bit tricky, you know, this bit tricky, but often we end up with this natural log function. And so how do I get y? How do I get from the implicit to the explicit, i.e. to the it? So effectively I end up with y equals e to the power of whatever is on the right hand side. And if you think to your engineering formula you've got, lots of times you end up with y equals or voltage equals or whatever, e to the power something, and it comes from solving a differential equation, modelling something like this, where my dependent variable is an inverse function, and so it occurs naturally, and that's where it comes from. So this is an explicit form we have here now, but we can play around with this a bit using our knowledge of powers. If I've got e to the one power plus another power using the laws of indices, I can write that as y equals e to the c times e to the x cubed over 3. So I can sort of take the c outside like that, and then I can call e to the c another constant. Let's call that k or something like that, or a. It's a common one. So, in other words, I can end up with y equals some constant times e to the x cubed over 3. It doesn't matter what form that constant is. It doesn't matter whether I write that constant as some e to the something or inside here. It's still a constant, but probably the most convenient way to write it is this. So that would be the best way to write our final function. This is our model that comes from the differential equation. So this is the explicit form. What we really want, in other words. Y equals something, our dependent variable. What is the relationship between y and x? There it is.